I'm Lucy Liu, and I'm currently a postdoc at American Museum of Natural History, and I will soon be moving to the Ohio State in the fall. So first, I want to say that I'm probably imposter because I mostly work on the Milky Way. So a lot of this talk will be based on the Milky Way, but then we're going to move forward to the LMC. So first, I'm going to motivate a little bit by talking about why we care about radial migration and birth radii, and a method to obtain stellar birth radii for stars in the Milky Way. And in the end, I'll talk about this method that we use to obtain birth radii for the Milky Way and how we can move that into dwarf galaxies such as the LMC. So birth radii is important because stars actually move around because interaction with the resonances or other effects that can move stars from where they're born and change their angular momentum permanently in the disk and change their radius over time. So one effect it's very important to take into is how this will affect how we obtain the metallicity gradient. So one example I'm going to give here is first, let's look at stars 5 gigayears ago. Let's assume that there's a ISM metallicity gradient that's linear, which is showing this gray line. And let's say that we form some stars in this metallicity ISM. And 5 gigayears later, we look at stars that are 5 gigayears old, and we can plot we can fit a line to it and say, okay, this is the gradient of the ISM 5 gigayears ago. So this is all good if stars don't move around over time. This is not true because they interact with other resonances, for example, and they scramble where the star is. So if you look at stars that are 5 gigayears ago and you fit a line, it will actually give you incorrect inference of the ISM gradient at that time, which typically will be flatter because there are more stars in the inner galaxy, so they kind of tend to move out. And due to these effects, you will get normally a flatter gradient. So if you look at individual galaxies and you look at individual stars and you try to infer these metallicity gradient from the ISM, you will have to take into account radial migration and birth radii. And just a disclaimer for people, LMC people, some people might think that, okay, LMC, it's a dwarf galaxy, maybe radial migration isn't that big of an effect, but based on simulation we see, you can still migrate around 0.7 kpc over 1 gigayear. So it is still important to take into account radial migration if you want to look at individual stars to infer metallicity gradient of the ISM. So this is seen in simulations and in the data. So on the left is a chemodynamic simulation showing metallicity versus radii for different ages of stars, which is showing in the dotted lines. And you can see that that looks really different for the ISM at that look back time, which is showing the solid line. So you can see that in order to infer the ISM metallicity gradient, you will need to take into account radial migration again. And on the right is showing the carbon to hydrogen ratio, plotting in birth radii space, which is showing on the left here, and plotting in guiding radius, which is current radius. And you can see that these different lines are showing the gradient in birth radii space and in guiding radius space, and they look really different. So again, all these is to show that it is important to take into radial migration. So what typically people do to get individual stellar birth radii is to assume that there's a linear gradient of the ISM at all time. So if you have a linear gradient, that means that you will need a point and a slope to define the ISM gradient at that age. So here on the left, for example, let's say we have a star that's 9 gigayears old. So what you do is you pull down a point, which in here is the solar neighborhood, metallicity, and then you pull out what the gradient is at that look back time, and you fit a line, and that's what you will say what the ISM metallicity profile looks like. So let's say you have a star that's 9 gigayears old and local metal rich, then you can slide the star back to its birth radii. And that's how you can slide a bunch of stars in the solar neighborhood back to its birth radii by using this method. So one big assumption here is that we have to know how the metallicity of a certain point in the galaxy evolve over time and how the slope of this ISM evolve over time as well. So one thing that we did last year is to understand whether we can get these two empirically. So we used ages from Rix 2022 and some Lemos abundances, and we're able to empirically obtain the inner galaxy metallicity profile over time, as well as the slope of the ISM gradient. So we use a simulation, and I don't have time to go into detail, but if anyone's interested, I'm happy to talk about it more. So what we found here, I'm just going to summarize a little bit. What we found here is that there is a direct anti-correlation between the range of metallicity of stars in mono-age population versus the metallicity gradient at that look-back time. So it's a way to relate the current day observable with what can be inferred from look-back time. So here is the red line is showing the Milky Way ISM metallicity gradient inferred from our paper. And here you can see that there is a steepening of this metallicity slope. And this is actually seen in some simulations if you pull in metal poor gas in the outer galaxy, and you can imagine that it increased the slope at that time. So we think it's tied to the effect of GSE. So we tested the same method on a simulation, and we see that we are able to recover the birth radii around 1.8 kpc. And what's interesting is that this is a constant scatter, it does not increase with birth radii. So which means that we're able to recover birth radii better in the outer disk for the Milky Way. And here on the left is showing the infer. So this is metallicity versus age and alpha Fe over Fe plane and color by different birth radii. And this is inferred, and on the right is showing the truth. So there's one thing I want to point out, which you can see a lot of detail is, for example, we can see that when merger happen, you increase in alpha and then it drops down. So we see a lot of features that's associated with merger signature. So I'm going to briefly mention what did pretty much the same thing with LMC, and we found that there are also two periods of time where the slope steepens, and it could be due to this merger signature with the SMC. And I'm just going to put this plot here, and eventually we're trying to do some multi-zone chemical evolution model on this and try to see if we can pull out more information. But this is just what the metallicity versus age, alpha versus Fe look like colored in birth radii. I'm going to leave it here. Thanks.
Awesome. Thank you, Lucy. We have plenty of time for questions.
Hey, Lucy. So I love this work, you know, right? But I am curious for the LMC. I just have this sort of gut feeling. It's not physically motivated, right? That somehow you wouldn't be able to do this just because it's so messy and it's much puffier. So have you have you tested this with simulations also?
Yes. Let me skip over a lot of slides. Sorry about that. Okay, yes, we tested this in the Nihao Suite simulation, which we found that even with mergers, with LMC mass, we should be there. Well, there should be radial migration signature, first of all, and we should be able to recover the birth radii. Oh my God, I guess I don't know which. Oh, here. So it's a complicated plot, but let's just look at things on the right-hand side. So here is plotting the dark matter mass versus how circular the orbit is. And this red line is showing the LMC, where LMC stands. And they're colored by how well we can recover the birth radii in the simulation using the method that we described. And here you can see that if you are over the LMC and you're kind of in a circular or circular disk scenario, I guess disky scenario, then you should be able to recover the uncertainty of LMC mass or above around like 20–25% uncertainty. But that is true that there is the SMC involved, and which could be making things a little more complicated. So we might look into a more LMC-like simulation to make sure that that is the case.
Hey, really cool talk. This is like the second or third time I've seen it, and it never stops getting cooler each time I see it. I wonder if there's anything you can say about the strength of radial migration in the LMC compared to other galaxies of that mass, or if you could combine your age metallicity relation with what you find to make some kind of quantitative prediction about the stellar ages as a function of where they are now.
Yeah, the last question is a very interesting question. I haven't thought too much about it. Yeah, I have to get back on that. But here on the bottom right is showing time axes versus the radial migration strength over time, and for the simulations. And you can see that they're colored by the total dark matter halo mass. And you can see that LMC mass, so basically if you normalize it by their scale length, then they kind of all sit in the same range. So for the LMC, we think that it's around maybe 0.7 to 1 kpc for 1 gigayear, but obviously it slows down over time. But yeah.
Okay, if we don't have any more questions, feel free to put them on the Slack, but we'll thank Lucy again. Hope I said that right. Yeah, okay, good. Yes. Okay. So that is the laser. Yeah, so it's Annalisa Leccia who will be talking to us about alpha element enhancement in the Milky Way clouds, ISM, evidence of recent star formation.
Thank you. I'm very excited to be with you today. I'm very thankful. I used to work mostly on the chemical properties of the interstellar medium at high redshift. And in time, I've been there redshifting. So this is my very first conference dedicated to the Magellanic Clouds. So I'm very excited about this. And just look at them, they're so beautiful. I stole this image from Scott Lucchini. It's an image of the gas. So gas is a fundamental ingredient for galaxy evolution and formation. And of course, it's super important for the Magellanic Clouds as well. We'll hear more about the gas from Andy and other people later on this week. I will focus this talk on the chemical properties of the interstellar medium in the Magellanic Clouds. Sorry, I'm too used to Magellanic, but you know, I can do the change. My brain cannot process yet. For me, they're very special because they're a unique laboratory to test the chemical evolution of galaxies, because that's one place where we can compare the chemical properties of the stars and the chemical properties of the gas. So as David said this morning, the interplay between gas and stars is fundamental for the chemical evolution of stars, of galaxies. So stars are formed from gas, different stars from different metals that are then recycled in the interstellar medium at different time scales. So they talked a lot already about supernovae, collapse supernovae and alpha element enhancement, so I don't need to explain this. But these kind of measurements are mostly done for stars. What about the gas? Do we know anything about this for the gas? So until recently, these measurements were not possible to do in the gas because of difficulties. But I developed recently a methodology so that we can do such measurements for the gas as well. So how do we do it? Well, first we need to do UV absorption line spectroscopy of hot stars and then get measurements of very many different metals. This has been done for tens of years, like very nice, but hey, there's like very big difficulty in really interpreting these abundances, because there's different processes that play a role in shaping the abundances in the gas. So we could have different metallicities, but we could also have the contribution from different stellar populations, like well, what I call nucleosynthesis signatures, like alpha element enhancements. Then we could have ionization effect, but in the neutral gas, this is less of a concern because most of the gas is neutral. And then there's the effect of dust depletion, and that's one of the most difficult to get around. So the dust depletion is the fact that the metals in the interstellar medium are actually missing from the observable phase because instead they are incorporated in dust grains. So until recently, the way to get around this was to just assume there was no variability in the metallicity, no contribution from nucleosynthesis signatures, no alpha elements, nothing. And the abundances, observed abundances in the gas were used as a proxy to study the dust depletion. Now, recently in the past years, I changed this and I've developed a methodology to constrain the dust depletion based on the relative abundances of metals, because different metals have different tendencies in incorporated into dust grains. And we can use these to characterize the amount of dust depletion. So we did this also with Christina Constantopoulou, one of my PhD students in Geneva. She used data from the Milky Way, Magellanic Clouds, and distant galaxies, and then characterized the dust depletion. So those are the dust depletion sequences. So this is the amount of dust depletion here, the delta, as a function of zinc over iron in the gas, which is a rough tracer for the amount of dust. So 0 means no dust, and here means a lot of dust. And you can see these sequences are for different metals. So the steeper these curves are, it means the more these elements tend to deplete into the dust grains. So now the slope of these curves are shown in the second plot here, which is, then you see the slopes of the depletion sequences, and overall it correlates with the condensation temperature. So now we have a way to characterize how much the metals deplete into dust grains. And we can use it to study the abundances and analyze the abundance patterns. How do we do it? In the following way. So now I plot, it's just like for us to understand how we do this analysis. So here we plot the abundances as a function of this refractory index, which is the slope that I showed you earlier, from the more refractory elements to the more volatiles to the right. So the panel A is, if you don't have any dust, then the abundances may as well just lie on a horizontal line, and that the normalization tells us the metallicity. But as soon as there's a little bit of dust, then the abundances of refractory metals goes low because they are depleted. And so the slope now tells us how much dust we have. And then you can focus on the third panel, which is then the addition of nucleosynthesis signatures. Like if you have specific stellar populations, then you can start seeing, for example, if you have core collapse supernova nucleosynthesis, then the alpha elements are all systematically on top of this curve. So the main trend here is shown by the solid line, and the alpha elements are systematically above, while manganese is below. So we did this for the Magellanic, so for the Milky Clouds, and a report here from this recent paper that we published. So we looked at 54 sightlines in the Magellanic Clouds from using HST's this data and the column densities from these papers. And we did the analysis that I showed you and found the ISM metallicity, the dust depletion, and the alpha element enhancements. And I will show you the alpha element enhancements. So this is a subset of our data set. And here you see the abundance patterns. So again, the abundances are on the y-axis. And then here you see the refractory elements. On the left side, you have the more refractory elements, and on the right, the more volatiles. And these panels are pretty much, well, they're very similar. So you can focus on, for example, one like that. So on the blue line, you can see the main trend. The normalization gives us the metallicity, the slope gives us the dust depletion. And then you see that systematically, all the alpha elements, these are the grounds in green, they are deviating, they're above this curve. Titanium, silicon, magnesium, sulfur, and manganese is systematically below. So we measure then the distance from this curve. So that gives us what I call the X over iron nucleosynthesis, because these are now measurements of the relative abundances after correcting for the dust depletion, and these can be directly compared with stars. So we did this for many different metals. Now, I will zoom in a few panels in a moment. So here we compare abundances of stars and abundances of gas. So for the gas, I use the yellow triangles and the blue diamonds, and then the abundances for the stars. And we have many different metals like magnesium, silicon, chromium, nickel, zinc, titanium, oxygen, sulfur, copper, phosphorus, and manganese. I know some of them are deviating or not reliable. Thanks. And for the first time, we can plot something like this and compare the chemical properties of the stars and the gas on the same scale. I zoom in on some panels so you can see the comparison better. So here are those plots for magnesium over iron, silicon over iron, titanium over iron. So it's alpha element enhancement for the Magellanic Clouds, and the same for the small Magellanic Cloud, and also manganese. And the points in magenta are the ones from apogee that we heard a lot about today. And the yellow points here are the measurements for the gas. And as you can see, the alpha element enhancement in the gas, it's always higher than what is observed in the stars. And it gets out to higher metallicities. Now, bear in mind the uncertainty on the metallicity is quite large. So don't take the metallicity there as it's not a well pinpointed measurement, but the alpha elements are better constraints. And also they're consistently high among the sample. And manganese is under abundance. Now, what does this tell us? How can we interpret this? Well, sorry. The alpha element enhancement and manganese under abundance point to a contribution of core collapse supernovae to the interstellar medium. So this could be the result of recent burst of star formation or bursts. When, I don't know, but we could compare to the young ages that have been observed, like in Tarantula Nebula, for example, or progenitor of supernova 87A, or the results from the star formation history that we heard, for example, from David this morning. So that's, I think it starts getting like really interesting. From the alpha element enhancement, in the gas, there seems to be a delay between the stars and the gas. So the stars could be, making the alpha elements, but then they recycle them, they throw them out in the ISM, but it takes time for the stars to pick it up. So they're not there yet. Will new stars have higher alpha over iron? Well, I don't know. Maybe it depends whether our results are biased. Remember, we are observing always OB stars. But it's interesting to compare already to the increase in the alpha, like this kink here that David and also Rachel have shown earlier for the Magellanic Clouds. So further modeling is definitely needed to try to make a coherent picture of the gas and the stars. So in conclusions, we characterize the chemical properties of the neutral ISM in the Magellanic Clouds and determine the dust depletion from the relative abundances is really key to disentangle the different processes and to really understand the neutral ISM. So the ISM metallicity is fairly it's fairly homogeneous with the exception of the Magellanic Bridge. I didn't discuss this, but you're welcome to ask if you like. And then we found ubiquitous, where we looked alpha element enhancement and manganese underabundance in the Magellanic Clouds. And this likely calls for a recent burst of star formation. Now, for the future, I think modeling of the chemical properties of stars and gas can be very powerful to further understand these systems. And from the data point of view, I think Ulysses has potential to map this even further. So I'll stop here and thank you very much for your attention.
Thank you, Annalisa. So while we ask the questions, can I get, yeah, thank you. So questions for Annalisa?
I was first, I think.
No, I've been asking a lot of questions, so I think he's trying to get me not all right away. It's up to you.
Either way, I'll be quick.
Rock, paper, scissors, no.
Hi. Okay, so Kat Barger, Texas Christian University. I was wondering, looking at the alpha to iron enhancements with the manganese, less underabundance over there. Have you looked at how those abundances are distributed, and have you done any comparisons between that and like the star formation history, the recent star formation?
So I didn't compare to the star formation history because that's something that we cannot really get. Well, okay.
From other studies.
But the distribution, because we really saw alpha element enhancement pretty much everywhere where we looked, then, it was homogeneous, but I can show you our lines of sight.
Sure.
So I think.
Because those galaxies are so bursty, I'm just wondering if we can get information about like mixing.
Yeah, so the circles are our lines of sight. Now, this plot shows the color coding shows the metallicity and where it deviates, like showing low metallicity. But basically, in all those lines of sight, we basically saw alpha element enhancements. And here is for the, let's see.
It'll be interesting if we can pull out any mixing information.
Yeah, and it would be nice to really being able to map this with, this is not so many lines of sight after all. You guys have thousands of stars.
Awesome.
Really nice talk. Kind of a similar question. I was wondering that alpha over FE offset that you see between the ISM and the stars, do you have enough young stars that you can subdivide the stellar sample and see if the difference gets smaller versus just the young stars? Or can you say anything about the timing of something like that?
No, I don't know the ages and nor the metallicities of the target stars. For me, the stars, well, they are background sources that allow me to, shine through the ISM and to measure it. Fantastic would be to actually be being able to measure their metallicities and their ages and so on. I think Ulysses has a more ambitious goal to also measure the metallicities, and so I hope we will be able to tell a bit more on that aspect.
Awesome. I think we're going to have to move on, but please put your questions on the Slack and we can carry on the discussion there. So can we thank Annalisa again? Okie dokes. So our next speaker is going to be Vern Smith, and he's going to be talking to us about stellar evolution in luminous red giants of the clouds from Apogee. Okie dokes. Away you go.
Let's see. Yeah. All right. Is this on? Hello? Yep, good. I want to thank the organizing committee for allowing me to give this contributed talk, and just say it's really great to be here at the workshop on the clouds, some of my favorite objects. And what I want to talk today about is the evolution of individual stars, focusing on luminous red giants in both of the clouds. And this is work that's actually really being headed by a graduate student of Virginia, Carolyn McCormick, who should be out there in Zoom land, I hope. This is going to be the foundation for her PhD thesis that she's working on right now. She's in the first year, working with Steve Majewski here, who was the original PI for Apogee. Katja Cunha is on this project, who's at Arizona. Chris Hayes, who's now at Space Telescope, and Thomas Masserone, who's at the IAC. And these nice pictures, here's the clouds here over Cerro Tololo. And here is just a snippet of a beautiful spectrum from Apogee. This is a luminous red giant. This is actually a Myra variable in the SMC. And you can get some idea of the quality of the spectra that Apogee can produce. And these are very, very cool, somewhat complicated spectra that I'll be talking about. And we've already heard from David and Rachel, this two really nice talks about chemical evolution. And I just show that here. There's, David's paper. You can see the starburst that you've already talked about. This is from Sten's paper, this huge, chemical evolution montage here. And the stars that were used in chemical evolution, typically in sort of, this is an H, J minus K diagram, are red giants. The spectra are a little bit easier to understand. There's not been as much stellar evolution, internal stellar evolution in these. Most of the stars I'm going to focus on today are the ones that were actually rejected. This is from David's paper. These are the stars he used. These are the stars he didn't use. But that's going to be the focus of the discussion today. So it's just a little bit of changing gears. And I'll start with an image of the SMC. This is a smaller sample, but it's a nice illustration of what Apogee has done looking at the clouds in terms of stellar evolution. So what I've plotted here is an absolute K magnitude. So we know the distance modulus to the SMC in this case. These are effective temperatures from the DR17 automated pipeline for Apogee ASCAP. And if you just take the Apogee sample, plot it without color coding, you get the lots and lots of stars. If you look at the positions, you can and there's nothing fancy. This is not done with AI. This is just done with the human eye. My own is to just start, you could look at this and make some guesses. You can break this up evolutionarily and say, this thing here, this structure is probably massive supergiants. The stars down here are RGB, first descent stars. This is the red giant tip. There's targeting in here too. There's always a selection function, but you do reach sort of the tip of the red giant branch. The stars in this regime here are various types of AGB stars. And then the ones that are very red are carbon stars out there, which are also AGB stars. They're just carbon rich. The C-O ratio is greater than 1. And you can't read this here, but there's a beautiful review from Amanda Caracas and John Latanzio on intermediate mass star stellar evolution. And they have this very nice synopsis diagram looking at sort of a function of mass, the different types of burning stages that go on in different mass stars as they evolve. And so you can see this very nice stellar evolution just splayed out here in the SMC. And you can see if your guesses make sense. If you can then go to isochrones, and these are missed isochrones, and put different ages so that you're looking at basically different mass stars evolving along these tracks. And indeed, you see there's a very young population. The most luminous stars fit pretty well with, say, 10 million year isochrones. So these are 20 solar mass stars, 15, 16 solar mass stars. There's a significant population moving on down. These are the massive supergiants. These are all in core burning phases of different types. As you go to lower masses and older stars, here we're at 100 million years, 200 up to a giga year, you see these tracks ascending past the RGB. This is the AGB. Then you get these wild excursions in the models, and these are the thermal pulses. So this is triple alpha burning, producing carbon-12 in the shell around the what will eventually be the white dwarf. And so indeed, you're seeing a map of stellar evolution spelled out really well in the SMC. And so one can use both ASCAP results that are automated, but you can also, do your own boutique analysis, which in a lot of cases for these complicated stars, you can do a better job. For example, Chris Hayes and Thomas Masserone, who are part of this project, took a lot of the spectra and looked at species that were hard to measure, things like rubidium or cerium, neodymium, and produced this catalog called the Bacchus catalog, where they went in and they did more of a hands-on, it's still an automated analysis on a subsample of the highest signal to noise ratios. In a sense, you can get for some elements, much better ratios, much better abundances. And when you look at these types of stellar evolution, what you should focus on is the different phases. So for stars that are RGB stars, they're undergoing the first dredge up. The elements are going to be altered by mixing, by the convective envelope, dredging material that's been exposed to various types of nuclear processes. These are the isotopes that will be most heavily affected during first dredge up. And I've colored in red the ones that Apogee can measure. And so you can use this data set to look at things like carbon-12, carbon-13, nitrogen-14, sodium, which is modified in the more massive stars during first dredge up. The minor oxygen isotopes are also modified, but Apogee can't really do a good job of measuring those. More massive stars undergo something called the second dredge up, much deeper, much higher temperature. You're going to get the same signatures as above in the first dredge up, but now oxygen-16 can be affected. Fluorine-19 is another mixing sensitive element. Apogee can't measure that. When you get to the third dredge up, you're bringing up primary carbon-12. Okay, these dredge up mechanisms really just cycle material around. They don't actually produce new nuclei of these species. They're really cycling them around from one to the other, changing the ratios. Third dredge up, you're bringing up new carbon-12 from helium, and you're also producing neutron capture elements all the way, starting with the iron seed nuclei, all the way up to bismuth. And Apogee can do a pretty good job of measuring both cerium and, to a lesser degree, neodymium. There's another phase in AGB stars where if the convective envelope gets massive enough and deep enough, you can actually cycle the primary carbon-12 into primary nitrogen. The nitrogen they produce here comes from the carbon-12. So this is referred to as secondary nitrogen. This is primary because the carbon-12 comes from helium. So you can see these enormous abundances of nitrogen in some of the more massive AGB stars. So this is all there that Apogee is capable of doing. And this is going to be the basis of Carolyn's thesis. She currently is working on a paper on the first dredge up stars, the RGB stars, but we'll eventually move into mapping this whole diagram. And I just wanted to show them the SMC was that one. The LMC, we have a much larger sample. And what I want to cover in this very short talk is simply to take some SMC stars, the sample here, and focus on just one strategic chemical abundance pattern, just so you can sort of see the type of things that you can do with the Apogee data set to characterize stellar evolution. And keep in mind that with the clouds, it was already mentioned in the previous talk, we have, it's a unique laboratory. We have well-determined luminosities. We have well-measured chemical abundances from Apogee. And so we can really produce, I think, the most detailed maps of certain phases of stellar evolution that have been done. Got it. So this is my wrap-up slide where I just took lots of colors and lots of tracks and things. But I picked the ratio of carbon to oxygen. That's an easy one. So this is really C12 to O16. And I've put the large cloud. This is the large cloud, the big sample, not the small cloud. The C/O ratio and luminosity. And again, color coded it. So these are the first ascent giants, the RGB. Here's the tip of the RGB. This mess here that I've color coded both kind of blue and black are AGB stars. I characterize these as early AGB. These are late AGB. The carbon stars are coded as red. And then these cyan points are the massive stars, supergiants. And I put my favorite models on here. For low mass stars, again, this is a bias, there's lots of models out there. I think the Lagarde models from the Geneva group, she's done a really good job of characterizing low mass stars. And so these black curves are Lagarde models. This is a 1 solar mass minus 0.6 metallicity. This is a 0.9 solar mass minus 2. And so you can see the C/O ratio changes from the dredge up, and it passes nicely through most of these first dredge up points. These are presumably even lower mass, more metal poor stars. If you put more models on, you'll be able to fit that. Marigo from the Padua group, they do a really good job for AGB evolution. They're probably the best in the world. And so all these red tracks are different mass AGB stars. This is about a 2 solar mass. This is maybe 4, you're getting up to towards 5, and then this is an 8 solar mass. And this is a beautiful illustration of what I just referred to as hot bottom burn. You can see that for the lower mass AGB stars, they produce carbon. You go up in C/O. Here's a C/O ratio of 1. So when you get above this line, you have true carbon stars. So they're the red stars in the large cloud right here. And these, again, these loops that you see are just the thermal pulses. But for the more massive models, this is an 8 solar mass one, you actually destroy the carbon. This is hot bottom burning, and you drive the C/O ratio down to very low quantity. So what you can discover in the clouds, for example, it's been known for sort of 30 years now, is that some of the carbon stars, the more luminous carbon stars in the cloud actually undergo hot bottom burning, more massive ones. There's a luminosity limit to carbon stars, and they become oxygen rich again from the destruction of carbon-12. So you can see this beautiful illustration, I think, of stellar evolution in the Apogee sample. And I'll just put my takeaway slide up and let it go with that. I will point out that this, I think, is a nice map for a Milky Way mapper, because the clouds are, the clouds are, we know the luminosity really well, not as, the stars in the galaxy are more problematic in terms of their actual distances. And you can also look for very peculiar examples of stars in the Magellanic clouds. For example, things like Thorne-Zipkoff objects that have been hypothesized. One has been claimed to have been found in the SMC. Rubidium is really the indicator of a Thorne-Zipkoff object. And rubidium is very difficult in Apogee, but if you increase the abundance by a couple hundred, which is what TZOs predict, you'll see it. And I'll leave it at that. Thank you.
Thank you. A great example of how Apogee is so versatile, and the clouds are really cool. Okay, questions for Vern? Encourage early career researchers. If not, I have a question. If we go back to what I would like to call the Dalí painting plot, which is that one, obviously. So you said that these are thermal pulsations, the horizontal lines. Could you, what does that actually mean? Well,
it means it's the helium begins burning unstably in the thin shell. And so you get an incursion in luminosity this way. So that's what drives that. And then
Your carbon stays and you just like,
well, the carbon then will dredge up. You have this,
but after the pulsation.
yeah, this is the thermal pulse, and then carbon will go up. And as hydrogen is burning during this phase of evolution, it's depositing helium under the shell. So the mass of the next shell is building up, reaches a critical mass, ignites, and burns in this thermal pulse. So it actually drives the luminosity down because it extinguishes the hydrogen burning shell. So you see, so this star is going up, hits the thermal pulse, the helium is burning in the shell, drops in luminosity because the hydrogen shell is disrupted. As the hydrogen shell burning, the helium then runs out, it stops. The hydrogen shell is reestablished, the previous luminosity is reestablished. That's when the dredge up phase happens, the convective envelope, which was forced upward during this helium burning phase, the shell burning phase. Convective envelope gets deeper and it dredges up carbon-12. And so you go up in this diagram, so you do these weird loops. Except here we have hot bottom burning where the carbon that is being produced is quickly being burned by to nitrogen by the convective zone. Cool.
Come back to you. I'm gonna go to Tanisha.
Hi, I have a quick question of how this will work observationally. Because things like HEP stars have these massive envelopes, right?
Mhm.
How do you separate out the effects from the envelope from the star?
Well, the interior, the nice thing or the cool thing about these stars is the interior nuclear burning material is connected to the surface through convection. So the surface abundances change dramatically. And so, for example, during the AGV phase, it's not just carbon that's going to change, but it also, during this phase of evolution, a neutron source is activated. It's carbon-13 alpha N. Releases free neutrons, so you'll get a buildup of the S process elements. So what one would expect to see, and hasn't been looked at yet, detail in the aptitude data, is going to be part of Carolyn's job, is that you should see the things like the cerium and the neodymium correlate with all of this AGV activity. And you have it's been seen in galactic stars for small numbers. It should be very easy to map in the Magi clouds.
Hi, I'm Joanna from the University of Surrey. Just out of interest, I might have missed this. So thermal pulse is quite difficult to model. I was wondering if you have tried other models with the thermal pulse and very late thermal pulse and seen how that affects things?
There are a lot of groups, and that, yeah, when one really sits down and does this, seriously and wants to sort of compare things, there are other groups that do say thermal pulses.
Mhm.
And I wouldn't say they're hard. I mean, there's a lot of physics involved that happens during thermal pulses, but there are a lot of groups. For example, I'm just illustrating the Padua group. Another really strong group would be the Australian group, which is Amanda Karakas and John Latanzio, do great work too. I picked these because these are easily available. All of these models, and these I forgot to mention, these are massive stars. This is from the Geneva group. These were done by Sylvia Ekstrom. These are models that are easily available online. You can just run, boom, boom. So you want to make a nice slide. This is great.
Okay.
The Australian group, for example, it's not as easy to extract their models as it is.
Sure.
Yeah. But there's plenty of models out there that you can compare to.
Cool. Thank you. Just out of interest.
Yeah.
More DALI plots, and we'll have a final question.
Hey, I just need to admit ignorance. What is a TZO?
Zitkoff object. And so it's either a merger of, if you have a neutron star and a red giant, you can get basically a stellar merger, and the modeling says that essentially the neutron star will sink to the center of the star very quickly. The thing will look like a very luminous red supergiant, and the bottom of the convective zone will be something like 10 to the 9 Kelvin. So you get this thing called the RP process. So you have a convective zone, you have hydrogen, so it's protons. R means rapid, because you're going to get fast proton captures. So there's a number of nuclei in the solar system. We all know about the R and the S. And for heavy nuclei, there's one called the P. They're very rare, the P process. They're P proton rich nuclei. These are a potential site for the P process. They're totally hypothetical constructs from Kip Thorne and Anna Zitkoff. But they've done calculations, and one of the predictions is that things like the two standout elements are rubidium and molybdenum. They both have P process nuclei. And we can't do molybdenum in the Apogee database. We can do rubidium. It's just not visible in most stars. It's very weak doublet transition.
Awesome. Thank you, Vern. Can we please thank Vern again? Yep. Look at this. Okay, so next speaker is going to be Andres Almeida, and he's going to be talking to us about exploring the origin of distance bimodality of stars in the periphery of the Small Magellanic Cloud with Apogee and Gaia, and more.
Yeah, and more, yeah. Well, as Danny said, I am Andres Almeida. I am a third-year graduate student at the University of Virginia. I'm working with Professor Steven Majewski and with more other collaborators. Yeah, I will be talking about this topic. This is a recently published paper we have. Okay. Okay, the outline of my talk will be just give a little bit of the background of motivation of the work, the data we use for this, present the results, the interpretation of these results, and also what is next, the future work for that. Okay, as we have been talking, Magellanic Cloud or Mickey Cloud or whatever they will be called in the future, a nearby laboratory of minor measures of interacting dwarf galaxies. Okay. Across the years has been detected several gaseous and stellar substructure around these small galaxies. Most of this substructure has been thought that it's come from tidal interaction, and some of them also, some gas might come also by ram pressure from the Milky Way. Okay. The motivation for this is follow-up of the work done by Dynevor like 10 years ago. You see, he used red clamp stars as standard candles, and he found, well, this is known before him, but he confirmed that, sorry about that. This area of the XMC, the eastern side, presented a bimodal distribution of red clamp stars, okay? Specifically, three of the region he studied show this bimodal distribution, whereas this found this foreground subpopulation of stars. Okay, the goals for understanding how this the origin of this bimodality, distant bimodality, is using a joint space of stellar kinematics and chemistry, and we will compare the properties of the SMC across other regions within the SMC. Data we use is Apogee to south, okay, stellar infrared spectra, which give us a very good measurements of radio velocities and abundances, and we combine this with Gaia DR3 proper motion as well. So here are the distribution of the Apogee field across the SMC, which most of them I observed. Okay, one of the challenges we face when we began this work is how we subdivide the SMC. The SMC, we know, is a very irregular galaxy. So what we will call the east, what we will call the center and the west. So we base our subdivision of the SMC in a shared joint distribution of distance, radial velocities, and proper motion. Being the red pointings, the eastern side, the blue, the center, and the green we call the eastern side, which is common like the western periphery of the SMC. Results. Our sample of stars were mostly RGB stars, which are not really good as standard candles. So we decided to use proper motion as a proxy for distance. And with this, we found this distribution of the proper motion-based distance, where the center and the west share a similar distance distribution, and the eastern side show a very peculiar or different among the other region of the SMC. So we decided to split this wing and to further see later if this property, this difference, can be traced also in radial velocity and metallicity. And it does. We have our RVs from Apogee. We apply a model from Civic for account to ball motion and rotation. And we find that the eastern side of the SMC seems to be approaching to us, approaching to the LMC, whereas the center and the west are moving in a more similar way. What happened if we subdivide the eastern side in a near and far subpopulations? It turned out that the stars in the near subpopulation are the ones who are approaching to us, while the stars we are so far behind this substructure are moving more like the rest of the SMC. Okay, fair result. What happened with the metallicity? Okay, we found that the metallicity in the east and the center are slightly more metal rich than the west. And if we look into the east near and east far, we see that the stars from the east far and the west are similar, more metal poor with a more larger metal poor tails, and the more metal richer stars are the east near and the center. Okay, what happened then with the abundances? The abundance pattern from the east seems like an average from the center and the west, okay? Which just we see a difference in the metal rich tail, I think. But we also try to see what happened with the near and far subpopulation. And we conclude that the trends, at least for the RGB star, are similar across the SMC, which say that have a common origin from the SMC. The main difference is in the high metallicity tail. So the interpretation of this, the stars, according to what we are seeing, are being pulled from the center of the SMC with the intense gravitational interaction with the LMC. A lot of this material, which lies from the SMC, constitute the nearest population, which is a way to explain the bimodality. So, field work. Right now, we are Apogee to South is over 2 years now. But we have the magnetic kinesis project for the CS5, which are we using this time the Apogee spectra as well, again, and the Bose spectra with AGB and RGB stars. The good news as we are planning to have a more continuous coverage of the SMC, so we can map the size, shape, and extent of this superstructure we are finding across the SMC. January 22nd, the coverage for the Bose was pretty good for the SMC. So we have some preliminary results. I use again the proper motion as a proxy for distance. In this case, I just been by 5 kiloparsec and see what happened across the SMC. And we can see that the eastern side shows the most prominent subpopulation of nearby stars, while the stars which are more the systemic distance of SMC are more evenly distributed across the SMC. So we are confirming what we found with less data. And for the radio velocities with BOSS, we are finding something similar, that the eastern side are coming at us, while and this time we will be able to see also some other features, what happens in the western side and the halo of the SMC. And that's it.
Thank you, Andres. Okay, questions for Andres? Seeing you, I'm coming to you.
Thank you for the talk. I have a question regarding how do you use the proper motion as a proxy for the distance, no? Because if I understood correctly, David found 10 years ago, no, that there is a bimodality on the distance because the red clamps is a good proxy for the distance. But then you found that red clamps is not a good proxy anymore, and then confirmed that you have a bimodality.
No, the red clamp is a good proxy. It's a good one. The problem is the RGB stars. I didn't have red clamp. I did have RGB. Not that good, not as great as standard Canon. We had some distances, but they were not that good. So we changed to the proper motion as a proxy.
Could you do this proper motion as a proxy, for example, for the LMC also? Have you tried that?
No, not yet, but we could. Yeah, I think.
Know the distances in the disk. So
yeah.
Okay, thank you.
That was going to be my question too. So hi, Andres, Claire Murray Space Telescope. Great work. I'm curious about both the proper motion distances, which I think are really interesting, and I think there's some interesting tests to be done there. But also if you have plans for doing similar work with other different stellar populations that you're going to get with Apogee in the future, like younger stellar populations.
You say within the SMC or?
SMC.
Yeah, we have new data now. We have a way better coverage. So yeah, we need to think how we will subdivide this SMC to find stuff interesting, I think.
Let's talk more.
Yep.
Hi, Cecilia Mateo, Udelar, Uruguay. Thank you for a very interesting, very nice talk. I was just going to follow up on that. Do you know if people have looked at this with RLR stars, or would you like to?
I know there is some work with that stars, but I'm not that familiar.
Because they're very good distance tracers, so they're really ideal to look at. SMC, are you kidding? No, but I mean to look at the distance by modality in our stars. I mean,
can I add to that? So the distribution of stellar populations in the SMC is really inhomogeneous. So the RLI ray, they are distributed more spherically, but the red clump has way more ages and metallicities in it. So in a way, it's a much better representation of that. So you can use RLI ray, but you would be tracing the sort of a spherical distribution rather than something a bit more inclusive.
something that only happens in a more concentrated population.
Which bit, sorry?
So this is some.
So
this is something that you would only see in the more concentrated populations, or
The bimodality?
yes.
Well,
I mean, if no one's looked at it, I agree
see
that
it in
it's
both.
unlikely that you see it, but
you can see it. I mean, I think it's just red clump's much better because it's got all the populations. So if there's a bimodality, so you've got a stellar population in front, a mix of it, and one in the back, then you see two red clumps on a CMD. So then you can see this bimodality. So with RLI array, you could see it too, but the red clump is just a much more point-like thing to look at.